Okay, so I'm going to be doing problem 10 from homework 2, and it reads, standing waves on a 1 meter long string that is fixed at both ends are seen at successive frequencies of 36 hertz and 48 hertz. A asks what are the fundamental frequency and the wave speed, and B, draw the standing wave pattern when the string oscillates at 48 hertz. Okay, so for part A, and this is homework 210, problem 10. So we're given some known values. The length of the string is 1 meter, and then the two successive frequencies, we'll call the first one frequency A, at 36 hertz, and equal to MF1, this is the initial one, and then the frequency that follows, frequency B, is at 48 hertz, and we'll make this M plus 1 because it's the following harmonic, i.e. successive, as stated in the problem. Great, okay. And so the first thing we want to find is the fundamental frequency. Okay, so we're going to take these two values and put frequency B over A, so we can solve for the fundamental frequency, and just plugging in what we have up here. One that matches up there, and then these two guys cancel, and that gives us 48 over 36 hertz, giving us 4 over 3. Oops, forgot that there. Yep. And M plus 1, we have that equal to 4m over 3 from above. There and there. Okay. And I'm going to multiply both sides by 3 to get rid of that. And that gives us 3m plus 3 is equal to 4m. And then subtract from both sides. 3 is equal to m. Okay. So because m is equal to 3, it means our frequency is at 36 hertz, giving us a fundamental frequency of 12 hertz. Okay. And okay, the second thing it asks is to find the wave speed. Sorry, just rereading the question there. So we'll take our well-known d equals RT, which is equivalent in our case to the wavelength being equal to velocity times 1 over the frequency, which is the inverse of is equal to tension. The inverse of the frequency is equal to tension, and we want to put our V out front so we can solve for that. And then, so the wavelength here, if you recall from our given equations, is equal to 2 times the length over m. So we'll plug that in for that. Okay. So now we can plug in our values, and because we're dealing with a fundamental frequency, our m value is going to equal 1. So we can just, and that being in the denominator, we can just knock that out. So 2 times the length, 1 meter, times the frequency, which was 12 hertz as we got from above. And that is going to give us a wave speed of 24 meters per second. Okay. And part B, let's do in the back. Part B is asking to draw the standing wave pattern when the string oscillates at 48 hertz. And so our f of 1, as we got from before, was 12 hertz. And I'll write this equation at the top just so you can recall. And f2, we're going to simply multiply f1 by m, which is this guy, being in the second harmonic. So that's 24 hertz. F of 3 is going to be 3 times 12 hertz, 36 hertz. And f of 4 is going to give us our 48 hertz. And so we're in the fourth harmonic. And again, this is the equation we used from before. So m is 4 in this case. And 2 times the length meter over the fourth harmonic. And that gives us 0.5 meter wavelength. And draw that out. And as you recall, this length here is 1 meter. And our fourth harmonic wavelength is half a meter. Oops, didn't leave enough space. That is our length. Okay, and then this section here is the half meter wavelength. And I think that's it. Awesome, thanks for listening.